And we're going to talk about the rest of this chapter. And we're going to go to the next chapter, whatever chapter that may be. We'll just pick one, why not? So I think we're still electrochemistry, I think. So last time, obviously, we got into a little bit more about our galvanic cells. So remember, got some sort of formulas there, right? Our E of our cell is equal to our E of our cathode minus our E of our anode. Remember, again, as we talked about a number of times last time, if you're going the subtraction route, you should not change the values that you find in the table on the SRP. That is what the subtraction will do for you, as the anode's always the one that needs to be basically changed the sign of. If you do want to change the sign, as we talked about, then you should definitely do more of the adding type situation here instead of subtracting these things. Don't change the sign and then subtract it, because I think you undo yourself in that case, which I think some of you guys did on the lab the other night. But I would keep, obviously, one method maybe and stick with it. We also saw our favorite thing, thermodynamics, our delta G minus NF of E. So remember again that if we have a positive voltage, that's going to result in a negative delta G, which will give us a spontaneous reaction. And vice versa, obviously, if we have a negative voltage, that's going to give us a negative and negative, a positive delta G, which means the reaction would be non-spontaneous. We also had sort of non-standard conditions there. Give the cell minus little RT NF natural log of Q on the Nernst equation. And again, maybe like we did in the lab, the concentrations are not all 1 molar, or maybe if you're dealing with some type of pressure, they're not all 1 atmosphere. So the Nernst equation is what we want to use. Remember, from the Nernst equation, at equilibrium, E would equal 0 and Q would equal K, which again gives us our equation that looks something like this. Log K. Bringing this entire thing to the other side gives us our other equation that relates to the equilibrium constant, which looks like this. Again, why we don't have the minus in that one as we do here. And again, since it is an equilibrium constant, same deal applies. Large value of K means that we probably should have some positive voltage and a negative delta G, which means it's all spontaneous. Small value of K means we probably have some negative voltage, and we also have probably a small value of K and a positive G. And again, all those things should agree. We talked about batteries and corrosion at the end there. Any questions on any of that stuff there? Obviously here, F is Faraday's constant, right? N is the number of moles of electrons. R is our gas constants, the 8.314 version, and T is our temperature in Kelvin. Any questions on that stuff there? All right, then let us talk about the last thing in this chapter, which is electrolysis. And electrolysis is the process where we apply sort of an external current of energy, and that causes a non-spontaneous process to occur. So for example, as you may know, if you take some sodium chloride and you heat it, you could heat the heck out of it and it really will not break apart. But if you do sort of heat it at a certain temperature, you can do that and apply a little electrical current that will allow it to break apart from sodium chloride into its elements of sodium metal, basically, or be a really liquid sodium at that point, and some chlorine gas. And also the same thing with water. You could heat water, it will just start to boil. But if you take like a 9-volt battery and run some electrodes over water, you can basically do a chemical reaction and break water into hydrogen gas and oxygen gas in this case. And I'll also do a little balancing here. And again, those are basically chemical reactions or chemical changes that are occurring in this case. It is the opposite sort of process that's occurring than when you put those guys together. So what do I mean by that? I mean by that is if we took our sodium metal, thank you, and our chlorine gas, and we made some sodium chloride, again, we'll put a, bless you, a 2 there and a 2 there. If we look at the oxidation numbers of what's happening here when we put it together in a synthesis reaction, that's 0, that's 0, that is +1, and that is -1. In this particular case, our sodium is our anode, and our chlorine is our cathode. But when we are rolling backwards and we take that ionic compound and we break it apart through a decomposition sort of reaction here, this is +1 and that is -1, and they actually go to 0. So going in the opposite direction, the sodium is actually going from +1 to 0. It's actually getting more negative, and it is our cathode on the backwards way. And our anode is actually our chloride ion here that is getting oxidized in this case. So it is reversed because, well, frankly, you're doing the putting together part backwards, right? So you're breaking it apart. So what was your anode going in one direction when you put it together is actually going to be your cathode on the back end. So that's what we see over here. We run an electrical current through here. We have our chloride going again from -1 to 0. And that is again becoming more positive and being oxidized, while our sodium is going from +1 to 0 on this side, again being reduced in this case. Again, the battery here allowing this non-spontaneous process to occur. Again, non-spontaneous means if you just leave it alone, it won't happen, right? If we leave water alone, it doesn't just spontaneously break apart into those things, right? So you have to do something, some type of intervention here by applying electrical current to cause electrolysis to occur. Speaking of water, here's an example of water. And usually when you do the electrolysis of water, which you can do, like I said, with a 9-volt battery and some electrodes and hook it up, and a little acidic water will do that. And you need the water to be acidic. It does provide a kind of bigger concentration of H plus there in the solution, and kind of helps out with the whole process occurring. By the way, when they do talk about sort of the electrolysis of water, a lot of times in books, they really just don't mention it's the electrolysis of water. They'll say something like they put an electrolysis cell together with some dilute sulfuric acid. So if you see some type of electrolysis cell that has some type of strong acid like sulfuric acid in it, they are probably talking about the electrolysis of water. So it's a lot of times they sometimes just don't come straight out and say that is what they're doing. And this again, in this case, when we have our water, our hydrogen is +1, our oxygen is -2, and it's going from -2 to 0 in this case. So again, if you follow that number line sort of approach like we talked about before, -2 is over here, ending at 0, becoming more positive, going through an oxidation here. And it's the oxygen in this case. On the other end there, we have our +1, really from the H pluses there in the solution. And that's going to go from 0. So again, in the case of the hydrogen, going in this direction, becoming more negative and going through reduction in this particular case. And that is what we are collecting in these test tubes here. The empty spot is really not empty. It is now red, but in that empty spot is our actual gases that we're collecting. In this case, hydrogen gas and oxygen gas happening. Why do I have more hydrogen and oxygen? Yeah, because it is H2O, so you got more hydrogen than oxygen. So you collect like twice as much in a lot of cases. And that's what we would collect in this case. So when we do electrolysis sort of problems, there are really almost a standard approach, kind of depending on which way you're going. They oftentimes will give you the current that the cell is running at in terms of amperage. They'll give you the amperage of how it is running and also how long it's running. They'll give you the time of it. And the relationship here is a coulomb is equal to an amperage times a second, which means if you solve for A, it is C divided by seconds, or coulombs divided by seconds. So usually a lot of times they'll give you how long they ran the cell for, and they'll give you basically the current at which they ran it. What you then want to do is actually use those two things. You would take the amperage, which is basically your current coulombs per second. You would times it by the seconds that you ran the cell for. The seconds would cancel, and that would give you your coulomb of charge that's happening. You would then use basically Faraday's constant to convert it from coulombs of charge into moles of electrons. And it's at this point you will have two half reactions like we just saw there, for example, for our sodium and our chloride there. Again, our chloride, right, going over to our chlorine. And obviously here we got a couple of electrons happening. And you would go to your half reactions and you will now have moles of electrons. And you basically will do a mole to mole relationship like stoichiometry. And you can see in this case, for every 2 moles of electrons, well, frankly, we get 1 mole of chlorine gas. So you kind of do like a little stoichiometry sort of conversion. What that would allow you to do is go from moles of electrons using the half reactions to figure out the moles of what you may be interested in. And in this case, I will now have moles of chlorine. At this point, it really does sort of depend on the question you're asked. Since chlorine is a gas, you may be asked what is the volume of chlorine that you may collect. So you may be asked volume of chlorine. And since it's a gas and you want volume, that probably should bring up a flash from the past, right? A little P equals nRT action, right? So you might have to use the ideal gas law sometimes in these cases if you're collecting a gas. Reminder that when you use the ideal gas law, the pressure has to be in atmospheres, the volume has to be in liters. This is moles. That is your temperature in Kelvin. And remember that this R is a 0.08206 version of it, not the one we've been using a lot lately. It is this version of it. So they obviously, if there was some type of gas situation, they would give you some of that other information like the temperature and also the pressure as well. So you would have that information usually given to you in it. Although they may not want volume, but they may want to maybe know how many grams you would collect. And in that case, going from moles to grams, that is the molar mass, right, from the periodic table. That's going to allow you to do that. So the ending part of this calculation is, it does sort of vary depending on what you're looking for. But those are probably the two very common endings to this type of problem, which is how many grams you may collect, or if it's a gas, how much volume of that gas that you may collect in that case. A variation on that sort of order is they will tell you something like how much you actually collected in the cell. And they may ask, you know, how long did you run the cell for, and kind of go backwards in the calculation. Or they may ask, you know, what was the amperage you ran your cell at? So kind of just going backwards. So usually these problems are either in one of two directions, going this way or kind of going backwards. But it's kind of very similar approach no matter kind of which way you're going. So let's take a look at one here together. We'll skip that one first. We want to know how much calcium will be produced in an electrolysis cell of molten calcium chloride if a current of 0.452 amperage is passed through the cell for 1.5 hours. So again, the first thing you want to think about is what is happening here. You do have to remember that we're actually starting with the calcium chloride in this case, and we're going to take this to its basic elements. And that's going to be some chlorine gas here and a little bit of calcium. And again, in this situation, the calcium on the left actually has a +2 charge and a -1 charge. The calcium on the right is 0 and 0 for the chlorine. So again, in this case, the calcium here is going from +2 to 0, which means it's becoming more negative, and this is going to be our cathode in the cell. The chlorine or chloride here is actually going to be our anode, as it's going from -1 to 0, becoming more positive. So that's going to give you your two sort of half reactions that are occurring. If I didn't write right over where that slid in there, so I just get rid of that there. Most of that there. There we go. So we have our two half reactions here, and obviously you do want to kind of make sure that your half reactions are balanced and you got the right sort of moles of electrons and stuff like that. So in this particular case, we have the amperage, which is 0.452 A, and that is the same as 0.52 coulombs per second. Because really that is in seconds, we would probably want to take our 1.5 hours and convert it into seconds. So 1 hour, there's like 3,600 seconds, I hope. And that's going to get me 1.5 times 3,600, about 5,400 seconds. Which, if I write it more correctly there, that would be better, I suppose. And now we could use our current of our cell, which is 0.452 coulombs per second. The seconds here are going to cancel each other out when we multiply them. 0.452. That's going to give us something like 24.40 or 0.8 coulombs. This is where we use Faraday's constant, which is at 96,500. So now that's going to help us turn this into moles of electrons. So again, 96,500 coulombs per mole of electron. Coulombs here will cancel, and that's going to get me, in this case, 0.0253 moles of electrons. Any questions so far in the calculation? At this point, this is where we're going to go to our half reactions. And in the case of the problem here, we're actually interested in the calcium. So again, we want the kind of mole to mole relationship from the half reaction. And we can see that for every 2 moles of electrons, we get 1 mole of calcium out. And that is the conversion factor that we're going to use to get us to moles of calcium. So for our 2 moles of electrons, 1 mole of calcium, that's going to get us here. Not that. Over there. Shock. Come here. 0.0253 divided by 2. Going to get us 0.01265 moles of calcium. We could go to the molar mass from the periodic table to convert that moles into grams, and that's 4008, I think, for calcium. Times 40.08, and that's going to give us 0.507 grams of calcium, in this case, would be produced in the cell. Any questions on that there? Now, if I was interested in chlorine, we could just really pick up this calculation right about here. And again, get our mole to mole relationship for our chlorine the same way. And if we wanted grams, we could use the molar mass of chlorine. Or again, if we were given some temperature, maybe some pressure information, we could go into the ideal gas law. Do you have a question? In the question, I think it asks basically how much calcium. So basically, we're looking for how many grams in this case. Yeah, it wasn't really specific there. So technically, you could have left it in moles if you wanted to. Yeah. Other questions? Okay. So I did that one. Once you tried the water one, yeah. So give that one a go here. So we're going to basically a current of 1.26 amperage is passed through an electrolysis cell there that contains sulfuric acid for 7.44 hours. What is the volume of gases generated at STP? So as you can see here in this problem, as I mentioned a second ago, it doesn't really say anything about water, right? But this is actually the electrolysis of water here because we do see the sulfuric acid. So again, for water, they sometimes just don't come straight out and say, hey, we're doing basically the electrolysis of water. So you don't have to worry about writing the half reactions, which we have already seen on the previous slide. So let's take a look. I'll just put them up here. So those are the half reactions. So basically, we're going to run this cell at 1.26 amperage for 7.44 hours. And we want to know at STP You know how much volume of each gas STP means? Standard temperature and pressure. Temperature is 273 Kelvin. Yeah, pressure is 1 atmosphere, right? A throwback question there, huh? All right. All right, give it a go. So basically here, oxygen gas, hydrogen gas, how much volume of each will I get? Okay, let's take a look. So again, in this case, since we're kind of given the amperage and how long we ran the cell, we're kind of going to go in kind of the forward direction here, working this problem. So I'm going to do a little bit of conversions. I'm going to get my seconds because I need that really in seconds so everything counts out correctly. So we got in hours, 3,600 seconds, and calculator says something. Let's see, 3,600. 26,784. This again is 1.26 coulombs per second. So that's really going to be my first time. I'm going to multiply those guys together. And that's going to give me really my kind of unit of charge there for this cell. So we'll do that there, 1.26 coulombs per second. And that's going to get us there 1.26 or maybe a 33747.84 coulombs. Remember, at this point, we're going to use Faraday's constant to convert us into moles of electrons. So 96,500 coulombs per mole of electron. So that's going to yield me in terms of electron moles, we'll call it 0.35, I think. Oh, moles of electrons. At this point, we can now really hit both gases separately. So we'll start with oxygen. Why not? So when we go to oxygen's half reaction, that is O2. So that is 1 mole of O2 gets me, looks like 4 moles of electrons. So we're going to use that. So our moles of O2 would be 0.350 moles of electrons. Once again, using the half reaction as a conversion factor, 4 moles of electrons, 1 mole of O2. And that's going to get me this guy basically divided by 4, 0.0874 moles of oxygen. We could do the same thing here for our hydrogen. So moles of hydrogen going into our equation. There is a 4 out here, and that 4, if it gets multiplied across, will essentially give us 4 moles of electrons is equal to 4 divided by 2, 2 moles of H2. That's also, by the way, the same as 1 mole of H2 gives me 2 moles of electrons. So you can really use either one if you want. It doesn't really matter. It'll come out mathematically the same. We'll go 0.350 moles of electrons. Again, you can use the reduced down version or really just the version you get. Again, comes out the same. Well, I'll use the one we get when we multiply. So 4 moles of electrons gives me 2 moles of H2, are the 1 to 2 relationship, which is essentially the same thing. And that's going to get me here 0.175 moles of hydrogen. Any questions so far? All right, so we have some of our gas information here, temperature, pressure, and R. We always have 0.08206 liters atmosphere Kelvin mole. Or if you like 0.0821, you can use that one too. So let's do our P equals nRT here. We're going to solve for V, which is nRT divided by P. And we'll do this for oxygen to begin with. So putting in our moles of oxygen, 0.0874, using our R, using our temperature, 273, and our pressure here of 1 atmosphere. That is going to get us here for oxygen collected I'll call it 1.96, and these are liters as Kelvins cancel, atmospheres cancel, moles cancel, leaves you just liters that are left of O2. We can then do pretty much the identical thing there for our hydrogen. The only difference here is we're going to use hydrogen's number, so we want to use the moles. Actually, everything else here is going to be the same in the calculation. So we'll use our R and our T, Kelvin, and our P, which is 1 atmosphere in this case. And for hydrogen there, that's going to collect us about 3.92 liters of hydrogen in this case. First off, any questions on that calculation? Could we have solved it another way? The answer is sure, why not? It's chemistry, so probably. Maybe you remember that because this happens to be at STP, there is a relationship that when you're at STP, 1 mole of any gas is 22.414 liters. So you could have kind of sidestepped the ideal gas law there and took, for example, your moles of hydrogen are either one of those and basically just use that in this particular case. And you would have done 22.414 liters is a mole. And again, that should get you pretty much there if you wanted to. Remember, though, if you want to use that, it does have to be at STP. If it's not at STP, you can't use that conversion factor, right? So that's what you can't do. We actually see here in this problem what we saw in the picture. It got me twice as much hydrogen gas collected, right, as I do oxygen gas, right? So again, here we see that occurs. Any questions on electrolysis type problems? Like I said, this is probably almost a standard type of calculation. Again, the variation on that is kind of going the other direction where you figure out either how long you run the cell for, or maybe what the amperage of the cell is. Any questions on that there? All right. That is this chapter, they say, I think. All right. We'll go with 18 because you seem very convinced that it is. So we'll go with that. So nuclear chemistry involves chemistry that's nuclear. Thank you. Good lecture. All right. So let's talk a little bit about radioactivity. Radioactive nuclei will spontaneously decompose, excuse me, into smaller nuclei. When something does that, it obviously is unstable, and it usually will continue to sort of go through a decay process until it kind of hits something that's a little bit obviously more stable. And we're going to talk a little bit about stability and what makes things sort of stable and unstable in this chapter. When we have something that sort of goes through a decay process, that guy that started it is usually referred to as the parent nuclide. And that one that's sort of kind of made as a result of it going through the decay process is sometimes referred to as the daughter nuclide. Usually a decay process such as this will result in emitting sort of radioactive sort of particles off as it's doing so. Obviously usually involves energy as well. If you look on the periodic table about after 84 or so, it's pretty much all radioactivity over there after that point. And that also takes you to kind of like the bottom row on the periodic table, where you get all the fun names, right? The made up names for made up elements, like your Einsteinium and all those kind of things, right? Your Nobelium and all those fun ones that are made up there. Your curium, your uranium is fun. I don't know if it's ever described as fun, but maybe not. I'll talk a little bit about types of radioactive decay. You remember your friend Rutherford? He did something with some alpha particles. Yeah, he shot them at some gold pieces of foil. That's usually the answer most people give, which is kind of like what I just did with the title of this chapter, right? What was Rutherford's gold foil experiment? Well, he shot like alpha particles at, gold foil. Did something. What are alpha particles? Well, alpha particles have the symbol of the alpha symbol there. They are basically positively charged radioactive particles. Frankly speaking, they are the friendly helium nucleus. Yeah, so they are the helium. And that actually in nuclear chemistry is sometimes used to symbolize an alpha particle. So if you see the helium there, that is an alpha particle symbol. If you see the alpha particle symbol, I'm going to go with that's an alpha particle symbol as well. So they are sort of used interchangeable. I am writing numbers on the top left there and the bottom left. That must mean something. Anyone? What is the top number? I was waiting for somebody to say 4, by the way, just so you know, that was the answer I was looking for, but no. The top number is what? That is neutrons plus protons, also known commonly as the mass number. Yes, that's what they call that one there. I'm gonna go out on a limb and go, they abbreviate that with an A occasionally, yes. And the bottom number there is the number of electrons. I'll go with protons. It is the number of protons, right? And that is the atomic number, more commonly known as. We'll go with a Z for that one. Why not? And again, the mass number, our number of protons plus our number of neutrons. Do you find both of those on the periodic table? The answer is no. Don't shake your head. Yes, it is no. You do not. Which one is not on the periodic table? It is this one. The mass number is not on the periodic table. The one on the bottom is not the mass number. It is the atomic mass. Yeah. The atomic number is on the periodic table. The atomic number is the important one because every element has its own unique atomic number, and it is the protons that is the most important thing, right? It is the one that determines what element you are dealing with, right? So you cannot have a carbon that has 9 protons because only fluorine has 9 protons as you go there. By the way, you take the mass number minus the atomic number, that is how you get the number of neutrons, right? So if you take your mass number minus your atomic number, that equals your number of neutrons. When you calculate neutrons, protons, electrons, mass number, and atomic number, they're all positive whole numbers, which is why the bottom number there is not the mass number, because most of those are all decimals, right? I felt like a really quick 200A review, I think. I don't know. All right. Beta particles or beta rays, they are essentially electrons, as they like to call them. And they have the beta symbol. Or because they're electrons, they like to use the electron symbol as well. And that's a 0 - 1 going on there. Gamma rays are pure radiation, right? You find that at the end of the electromagnetic spectrum for our 200A throwback day. And that is that the very short wavelength, very high in energy, past X-rays, right? Which is, again, you should be super careful with them. They have the old gamma symbol. Yeah. Zeros on top and bottom there. In addition, there are other particles that we come across here in nuclear chemistry. We have positrons, which is frankly an electron with a better attitude. Thank you very much for the courtesy laugh. I like it. So a positron is actually a positive electron. So confusingly enough, it uses the same symbols, but it's +1 instead of a -1 there, right? So that's a little bit different, I guess. Now, how do you know if it's a beta particle or a positron? Well, if it's a positron, they usually will put like the positive symbol in there, even if they kind of just, basic it out. If it's just a beta symbol like that, you can probably assume it is a beta particle. If they do something like that, they most likely would do something like that as well to let you know maybe it's a positron. Yeah, they would put the positive guy in there for sure as well. In addition, sometimes we do have some reactions here in nuclear chemistry that capture an electron, and it is pretty much what it sounds like. It's an electron that gets captured. It is on the sort of reactant side. When we talk about sort of equations and nuclear equations, there are some words that sometimes occur, like it emits this particle, or it gives off this particle, or goes through this type of decay. That means that those particles end up on the product side of the equation. If it says it's been bombarded with that particle, or it undergoes some type of capture, those particles are on the reactant side. So that's some terminology that's sometimes used. There was the slide with the review. There it is. I think we got that right. Some other friendly particles that come by in our nuclear situation here. Doesn't sound good either. All right. There it is. A proton is oftentimes used, and a proton, by the way, has one proton, right, which is hydrogen, and it has one electron and has no neutrons, hydrogen, right? But for a proton, it is sometimes used as a P or a hydrogen. And also one that's used a lot in nuclear chemistry is a neutron. So a neutron, N is used for a neutron, 1 on top, 0 on the bottom. And again, this is sort of how they change in our mass numbers and our atomic numbers. Now, when we talk about these different types of rays, they do penetrate your tissue and lead, for example, different distances. You can see alpha particles, not super bad. Beta getting worse. Gamma rays, not so great. And depending on if you ever are working with anything that's radioactive, you may want to make sure you understand what type of emitter it is, so you take the proper protection for yourself, just in case some people forget to give you the important thing, like, hey, you probably shouldn't be standing over that all day and watching it just like hit you with particles. So sometimes you just need like some gloves and a lab coat, and sometimes you need a lot of lead and some distance and some safety between you and those things. So obviously our gamma rays emit and go very, very far into tissue, and beta also goes pretty far. Alpha, not so bad. Here's some of those symbols again, in case you, you know, didn't like the first ones. So let's talk a little bit about balancing nuclear equations, which is like super hard. It's really not, as if you know how to add, I suppose, is all you pretty much has to do. So one of the major differences, as you should be aware of, between nuclear reactions and chemical reactions is, in a chemical reaction, all we do, right, is break bonds and make bonds. And that's all about electrons, right? We never touch anything in the nucleus, right? And because we don't touch anything in the nucleus in a chemical reaction, we have the conservation of elements, which means if we started with 4 carbons, we should end with 4 carbons on the other side of the arrow. Now, in nuclear reactions, it's all about the nucleus and playing with protons and neutrons and changing protons into neutrons and neutrons into protons. So we do not have conservation of elements in nuclear reactions. So you start with one element and you make a bunch of different things along the way as this thing is going through these reactions and going through a decay process and stuff like that. So because we don't have conservation of the elements in nuclear equations, to balance a nuclear reaction or equation, we actually just need to make sure 2 things are met. On the left-hand side of the arrow, you need to make sure when you add up all of your mass numbers, which are up on top, they need to equal all the mass numbers that are on the right-hand side of the arrow. So in this case, we add them all up there, 236 on the left and 236 on the right on top. By the way, this neutron does have a 2 as a coefficient, which means you do need to multiply it by the mass number and the atomic number as well. So that's how we get basically a 2 for that guy up there on top to get us to 236. The other thing that we do is to make sure that it's balanced is, frankly, we make sure the atomic numbers that are on the bottom there on the left match the atomic numbers that are on the right. So that is how we balance a nuclear equation. So what would happen? So for example, if we have this one here, and let's just say that something was missing. We'll just take like our guy there, 855. And then a couple of neutrons happening. So let's just say this guy here was missing. The approach you should probably take is, out of protons, electrons, and neutrons, as you mentioned a second ago, which one tells us which element it is? The protons, right, are the atomic numbers. So that's probably where you should attack first. So we would want to add up our bottom here and go, okay, I got 92 for my atomic number on the left. Over here, I got 55 and 0, which is 55. I do a little subtraction there. That's going to get me 37 is my missing atomic number. Then you go grab your friendly neighborhood periodic table. That apparently has a Dodgers like symbol on the back of it. Clearly water was in here. All right, so you find number 37 right there. And I should really put some Padre symbols on some of these, and that way when he grabs them. So 37 would be our guy there, RB. And that would tell us obviously what element is missing in this particular case. Then you could do the same thing for the mass number. If you add up the top, obviously here we have 236 on the top. On the other side, we've got a 138. And like I said before, since there is a coefficient here, you do have to kind of times them together. So we would want to subtract off the 2 and not just 1 in this case. And again, that will give you, obviously, as we can see on the bottom there, our missing mass number of 96. So that is basically the approach that you want to take to find something that is missing. And sometimes you are just given like the starting guy, and you're asked basically what type of decay, or tells you what type of decay it happens. So this is what I was talking about before. If it says, hey, this thing goes through alpha decay, then you would put the alpha particle on the right-hand side and then start doing your math and try to figure out what the missing atomic number is. You should be aware that it may, in some cases, in some problems, may actually be a particle that's missing. So if you kind of add something up and you go, it doesn't really match somebody on the periodic table, then it might be, you know, maybe some type of particle that is the missing piece of the puzzle. But I would say probably 99 times is going to be somebody off the periodic table. So why don't you try that one there, PO 212, write the balanced equation for this reaction here. PO is, I think, 84 there. Okay, so let's take a look. So the top number obviously is the mass number, and that is what we are starting with. Again, you would probably want to go to the periodic table there to find the atomic number here, so you have all your numbers. This decays by alpha emission, so that means that's an arrow, and we want our alpha particle, which again, you could use the alpha symbol, or if you wanted to use helium, that is all good as well, whichever one that you want to kind of put in there. So now that we have sort of everything that's there, we could kind of, you know, figure out what is missing here, basically. So on the left-hand side here, in terms of atomic number, we have 84. Right-hand side, we got 2, so I'm going to subtract that. That is going to give me an 82 as my missing atomic number. I will then go to the periodic table and find number 82. That is our friend lead, I think. We're going to do the top guy there. That's a 212 on the left-hand side. We already got 4 on the right-hand side. That's a lot of math. 208, I hope. Yeah, so I'll go 208 there. Without the 8 of the calculator, we hope for the best there. Yeah. Any questions on how to do that there? Not too bad. Just add calculator and a periodic table. Should be good. We should just have the final that does all this, right? I suppose so. Final exam. Yeah. All right. Do they agree? Hope they agree. That'd be kind of embarrassing if they didn't agree. That's good. All right. All right. So as I mentioned a second ago, there is a major difference, obviously, between chemical reactions and really nuclear reactions. And as we talked about before, chemical reactions really do involve just breaking and making bonds. That's all electrons. And as I mentioned earlier, nothing in the nucleus gets touched, so we get that conservation of elements. Here, as I mentioned, it's all about the nucleus and what's happening in the nucleus. So we do get a lot of changes that occur in what we start with and what we end with. Now, a beta decay process, talk about a few of these processes here. A beta decay will decrease the number of neutrons by 1 and increase the number of protons by 1. And that's what we see here. We go from carbon 14 to nitrogen 14. Mine 6 to 7 beta particle is -1, so we actually have to do one more above. That's a neutrino. We're not going to worry about it. It really has no mass or anything like that, so you don't have to worry about that guy there. So what is really happening in this case is actually in this process, one of the neutrons gets converted to a proton, and it will then also make a beta particle that's being emitted on the product side. So when you have a beta decay or beta emission, that is a result basically of a neutron being converted into a proton, and the offshoot of that is the beta particle basically is coming out. The mass number doesn't change here, even though we do lose a neutron. And it's because if we kind of did it in a stepwise fashion, which is obviously not super correct, but we'll just talk about what's happening here. What's basically going to happen is we're going to lose a neutron, which means we're going to lose one off the top there, which then takes us to like 13 and 6, right? We then will make a proton, which means we're going to add one to both of those guys. And that takes us back to 14 and 7, and now nitrogen in this case. And now it releases that beta particle. So the mass number really does change, but it ends up back where it started with, is basically what's happening in this process that's occurring. When we have a positron emission or a positron decay, remember, a positron is basically like a beta particle, except it has a positive charge. So in this case, again, overall, the mass number kind of stays the same, but we do decrease the atomic number by 1. The reason for that is in this process, we're actually converting a proton into a neutron in this case. So again, the same sort of things happening. If you just kind of think of it almost like a step-by-step process, when we lose the proton, we subtract 1 off of each of those. And now we're at 10 and 5, and that's basically what changes now into boron. But the result of that is we actually throw back a neutron, which adds 1 to the top. And now we're back to 11, 5, and boron. Again, overall, no net change of the mass number, but we are swapping, basically, in this case, a neutron for a proton. So there is that change that's sort of happening. Any questions on that there? Electron capture, as I mentioned before, is the process where basically somebody grabs onto an electron, and that is actually going to be more on the reactant side. So here we're just really adding. So 18 and -1 leaves us 17, which takes us to chlorine. In this case, what's happening is the proton and the electron are coming together, and it's going to result in the formation of a neutron in this case. And once again, there's not going to be a change in the mass number, even though there is. So again, same situation, 37, 18. We're going to lose a proton, which takes 1 out of each. We will then gain back an electron, and we will then gain a neutron up on top. So that is a net, nothing changes up on top. And that is also what we're going to end up with here at 17, as obviously we will subtract 1 to 17. And in that case here, we don't really need that there because we already did it. And we'll end up with our 17. Our alpha decay is really the one that will make the biggest change. We're going to change by 4 and 2. And that is our biggest sort of change that occurs. Now, when we have a process of fission, fission is the process where an unstable nucleus will basically break apart into 2 new nucleuses, and usually will release some neutrons. And also, by the way, a good amount of energy is going to probably come off in that process as well. Now, fission reactions can be spontaneous, like this one here, which means it will just spontaneously do that or go through that process. You could also force something, in a sense, to go through a fission reaction. And you could do that, for example, like shooting a neutron or some type of particle at a stable nucleus. Kind of makes it a little upset when you do that. And then it becomes unstable, and it'll actually go through the fission process. That is like, you know, that is the reaction, for example, that's used in nuclear power plants and nuclear bombs and stuff like that as well. Yeah. Yes, sir.
They were originally scared about the atomic bomb being set up with these chain reaction.
Yeah, we're gonna actually talk about that a little bit later on, but yeah, so if you do not keep it under control, it can be a never-ending cycle. And because what in that case of that situation is, they basically will use a neutron to kick off that reaction. And what happens is this guy will then split off into some new guys and make a bunch of neutrons in the process, which now, if you have the right amount of everything, could kind of swing back around and just keep doing this process over and over and exponentially growing. And every time it does this process, it releases an enormous amount of energy, not to mention all the byproducts that are quite radioactive along the way, which is not good for a long period of time as well. So that's the idea behind that and stuff like that. And we'll talk about that a little bit later on in this chapter and how they sort of keep things under control. So hopefully that don't happen in a nuclear power plant, obviously. Here's a picture in case you didn't like all the other stuff that we were talking about there. All right, why don't you try this one here? Write the nuclear equation for the positron emission of potassium 40. That 40 would be which number? The atomic number and the mass number? Well, I'll give you a hint. If you go to the periodic table and you find potassium, I believe it's 19. So that number is the mass number. Yeah, so that's a very common way isotopes are written. The symbol dash a number, and this number is actually the mass number. So we'll start with our symbol here, 40 being our mass number. Off the periodic table there to find our atomic number. This is a positron emission. So emission means product side. Positron +1 beta symbol, or you could use the E symbol as well for like an electron. So in this case, looking at our atomic number there, I think we need an 18 there to get us to 19 on both sides. Going to the periodic table, number 18 is our friend argon. Up on top, I got 40 on the left, 0 on the right there. So that's a 40 spot right there. And there it is, yeah. Any questions on